Okay, well, thank you. First, I'd just like to thank Anil for organising this meeting in the first place. It's really a pleasure to be invited to talk about some of this work that we've been doing. I'm Christopher Burgess. I'm from the University of St Andrews, and today I'll be talking about work that I've been doing with my supervisor, Frida Koenig. I'm from the experimental optics group at St Andrews, and we've been working on analog gravity with optical solitons. And the optical soliton is in a non-relativistic system. Its perturbations obey a Schrödinger equation. And so we got interested in trying to calculate the quasinormal modes of the Schrödinger equation. And this is really work that's stemmed from that. So this talk is going to be based on a couple of papers. One, which is calculating the QNMs of the Schrödinger equation analytically for the optical soliton. And another is what this talk is mostly based on, which is generalizing the hyperboloidal method in order to be applied to the Schrödinger equation. And I'll also attempt to say a little bit about going beyond the Schrödinger equation as well. Okay. So the structure of this talk, I'll begin with a review of quasinormal modes and solving the relativistic problem, so the wave equation, using this hyperboloidal method for the wave equation. Then I'll move on to the main topic, which is talking about the Schrödinger equation and how we generalize this method. And then I'd like to say a little bit more, as I said as well, about going beyond the Schrödinger equation. So that's looking at generalized wave equations and how we define the QNM problem in that case. So for review, I talk a little bit about quasinormal modes. So we're all familiar with normal modes. We have a system, we can do a separation of variables. If it's a conservative system, then we end up with mode solutions which are periodic. These are described by real frequencies, so we have a real eigenvalue. We have a spectral theorem, and we can do a complete expansion of the field in terms of these normal modes. In the case of quasinormal modes, by analogy, we now have a dissipative system, and so we can still do a separation of variables, but now this time part is decaying, and this means we're describing it with a complex eigenvalue, where the imaginary part is describing this decay rate. We no longer have a spectral theorem, and we can't do a full expansion of the field in terms of these quasinormal modes, but we can do a partial expansion for sort of the dominant part of a perturbative response, and this is a so-called ring-down expansion. So these are quasinormal modes. The pictures that I have here are sort of an image of a plucked guitar string in a sort of idealized frictionless case. You have the normal modes on the left. Problem is that you can't hear that guitar because it's not coupling to the air. In the case of quasinormal modes, then it does couple to the air, but that means you have dissipation. And this dissipation everywhere on the space is going to lead to a sound that gets dimmer and dimmer, or less and less audible as you go on. So that's the case where you have dissipation everywhere on the space. But what we're really interested in the astrophysical context, and also in terms of solitons in the lab, is we're interested in wave equations. And these are conservative wave equations. So we might ask the question, how can it be that a conservative wave equation, which doesn't have any dissipation, nevertheless is going to have QNMs? And the answer to this question is that it's all in the boundary conditions. If we have outgoing modes, and we have modes that aren't falling off to zero as we go outwards, then we effectively have dissipation at the boundary of our system. So we have energy leaving our system at infinity. That's the basic idea. So what I'm going to look at now is how we calculate these quasinormal modes for a wave equation for a given potential using this hyperboloidal method. So before we do that, I need to state what the problem is. So there's a little bit of information here about what the boundary conditions actually look like. So we start with the wave equation. We take a mode ansatz because we're interested in quasinormal modes. And then the boundary conditions are going to be such that as we go off to infinity, the field is simply propagating outwards. And in a relativistic system with a relativistic wave equation, there's no dispersion. And so the field evolves in a very simple way. It's just simply translating as you're moving outwards. And so because that's very, very simple, you have this very simple boundary condition, which is just this simple relationship between the wave number and the frequency. And if you have that relationship, then the velocities are outwards, and those are your QNM boundary conditions. So applying this compactified hyperboloidal method then, so this is going back to work that Anil did, started off in 2011, I believe. And this is sort of the progenitor of this coordinate transformation, this compactified hyperboloidal coordinate transformation. There's also a very nice paper by the Yaramillo group in 2021, which lays this out very nicely. I enjoyed that review. And if you go through this, the main idea of the coordinate transformation, as I see it, is that you want to squash everything down so that you have a finite domain to work on. because that helps you to discretize your domain. But in doing this, you need to make sure that your fields are finite everywhere on the space. So one of the features of these quasinormal modes is that they blow up as you're going outwards in space. The reason for that is because they decay in time, and their behavior in space has to be opposite to their behavior in time because it's relativistic. And so that means they have to diverge as you go out in space. And so squashing it down just on your R coordinate isn't going to work because you'll end up with divergences at the boundaries. So the idea of this hyperboloidal transformation is that you're going to map along contours where the solution takes a finite value because it's not changing as you go along these light cones. And then you can squash that down and you have a field that's finite everywhere. You can then perform a reduction in time by introducing this auxiliary field psi. Then you arrive at an eigenvalue equation. You can discretize that using your preferred discretization scheme, and then you employ whatever your favorite numerical solver is, and you can extract the QNM spectrum in that way. So this has been used with great success in lots of different places. So it's been applied a lot to the partial telepotential, and I'm going to join in that rich tradition by applying it to the partial telepotential again today. So on the top left here, we have the raw partial telepotential, then we have a parameterized one, and then a perturbed partial telepotential. So there's this nice work on pseudo-spectrum that's being connected now. And of course, black holes as well, which is what this method is really born for. So just to go through in some detail then, so the coordinate transformation, as I said, the idea is that we want to choose these spatial slices to correspond to contours of constant field asymptotically. And one of the key parts of this transformation is that the partial derivative in time doesn't change, meaning that the frequencies we extract at the end are actually the original frequencies we were interested in. And as I say, the QNM solutions, which are normally divergent, end up being finite everywhere on the space, which is essential. We perform the reduction in time, and we arrive at an equation of this form here, with purely spatial operators L1 and L2. Then we get an eigenvalue problem, and it can be shown that this eigenvalue problem is self-adjoint in the bulk and non-self-adjoint on the boundary of the space. So if we think back to the picture of the guitar string that we plucked, that had dissipation everywhere. Here we just have dissipation at the boundaries, which is what we expected because we sort of squashed in infinity, brought that in, and that's why we have dissipation. We then discretize that. The preferred method of discretization is Chebyshev discretization. So that's using these Chebyshev extremal points. This is basically a polynomial interpolation method, which replaces derivatives with these Chebyshev differentiation matrices. And then we apply a numerical solver, and then that's how the method works. This is at the end of that, having solved this this eigenvalue problem numerically, we get out a QNM spectrum. So that's sort of how things go in the relativistic case, as I see it. I'm now going to start talking about how things go in the case of the Schrödinger equation. The sort of the headline is things go very, very wrong very, very quickly, but we can fix it up. That's the idea. So sort of motivations first. Why are we interested in this? Well, there's a sort of intrinsic interest in being able to say something or do something new with the Schrödinger equation, obviously a very famous equation, so it's a nice equation to work with. More down to earth, my group or Frieda's group, our group, has an interest in analog gravity. And so we work with the optical soliton. The optical soliton obeys a nonlinear Schrödinger equation. Its perturbations obey a Schrödinger equation. And so since we can make, in particular, the soliton is a partial telepotential for this probe light that goes in. And so it makes for a nice mode analogy with black holes. And so being able to calculate the QNMs of this is an interesting problem to want to tackle. In Bose-Einstein condensates, you get a Gross-Pitievsky equation, which reduces to a nonlinear Schrödinger equation. So you have similar physics going on there. And also this is within analog gravity. So this is an interesting problem where, again, you would end up with QNMs of the Schrödinger equation. And then another interesting problem is this question of black hole spectral instability. One of the ideas behind doing experiments in the optical soliton is that by having an experimental system where you can look at QNMs, you can actually do experiments and investigate these black hole spectral instability questions with experimental tests. And then one of the overarching goals is to start applying these methods in non-relativistic systems so that we can move to higher derivative theories. So there you have models of quantum gravity where higher derivative theories occur. These are models with Lorentz violations and things like that. And also this is useful if you want to model experiments in a more realistic way. So all of these physical systems that we have in the lab, they all involve higher dispersion in some way. And so being able to accommodate that into your theory and then see what happens to the spectrum is essential for modeling experiments. Okay, so the problem statement for the Schrödinger equation then, for the QNMs, we start with the equation, we take a mode ansatz again, and now we want to impose the boundary conditions. When we're far away from the potential, we have these plane wave solutions again, and we want to say that our field phi is outgoing. But it's a little bit more subtle now what we mean by outgoing. For the relativistic case, since all the velocities are the same because it's non-dispersive, the phase velocity and the group velocity will mean the same thing, so it's very easy to talk about what outgoing means. But for a dispersive system, we could ask, well, do we mean the phase velocity or do we mean the group velocity? The way that we answer this question is by appealing to a continuity equation. So we can construct a continuity equation from the Schrödinger equation, and then we have a conserved quantity, which is the integral over the density, and then we have this current. And so we judge that the natural way to impose these boundary conditions is by taking this conserved current and saying that conserved current should be directed outwards at the boundaries. And it turns out that this is the boundary condition that corresponds to the, if you like, corresponding boundary condition in the wave equation case. So it will generate a spectrum which is related to the wave equation spectrum in a way that I'll discuss in just a moment. So yes, so yeah, the condition is that the sign of this current should be positive on the right and then negative on the left. Yeah. Okay, so I said that there's an analogy to be drawn between the relativistic and non-relativistic case. It's a very simple analogy that's been observed before. So just at the level of modes, you can see that these two equations are essentially identical to each other. If omega was a real quantity, then there would be some big difference here. But because omega is a complex quantity, there really isn't much in just a square. It doesn't really make much difference. It's still complex. So the spectra of these two are going to be related to each other in a quite simple way. So if I have the relativistic wave equation with a given potential V, and I calculate its QNM spectrum, then I can obtain the QNM spectrum for the non-relativistic system just simply via a square root. So there's not much in it. It's very simple to go from one to the other. This is if you're taking the boundary condition that we just gave with the continuity equation. So this being the case, the real import of this method isn't quite so much getting out the spectrum. That's not quite it. What it is more about is being able to apply this method in a direct way without employing this analogy in order to see the problems that we encounter along the way, so that in solving those problems, we know how to generalize beyond the Schrödinger equation. Because of course, you know, the vast majority of systems are non-relativistic, you know, just at the level of mathematics. Okay, so I'm going to start off with a sort of naive approach, which is just going to be to do everything exactly the same and then see what happens. And ultimately, it's not going to be as simple as this, it turns out. So we can apply the coordinate transformation. The only difference here is that instead of having a d tau squared in this equation, we end up with an I d tau, whose origin is fairly obvious. We can then do the reduction in time. We again arrive at these spatial operators L1 and L2. We get an eigenvalue problem. We can discretize that in the same way as before, and we can solve it. We do all of these steps, and we get out totally spurious results. So what we find is that as we increase the resolution of our discretization n, we don't have stable results. We just have a mess that's all over the place. We get a bunch of points in the complex plane that don't really tell you anything. So there's something wrong with this approach. People in the audience right now, probably some of you already have in mind what is wrong with this approach. So we'll see if you're right. So one of the big problems is that in a non-relativistic system, there's no preferred speed. So in a relativistic system, the reason this transformation worked and made everything finite was because asymptotically, everything was traveling out with the same speed c. But in a non-relativistic system, because of our non-trivial dispersion relation, we now can have any possible speed available. And so in particular, if we plotted different QNM solutions, we would see that these are moving out with different contours of constant amplitude as we're moving out asymptotically. And so that in these plots, that's the different angles of these lines. So the consequence of this is that there's no unique coordinate transformation which is going to capture all of these QNMs at the same time. So if you did capture one of them, what you would end up with is that the others would either vanish to zero or they would diverge. And so that's the reason why the method was giving out nonsense answers. It's because the fields weren't finite anymore. So the way that we get around this problem is we parameterize the coordinate transformation. So if you simply insert a parameter in front of the height function, and so this h naught here in the height function is now the relativistic height function. If you insert a parameter in front of that, which I'm calling Vg, sort of suggestively, then this parameter is controlling the effective speed of the contours corresponding to your height function. So there's a speed because you have a contour in r and t, and so that defines a speed if it's a straight line. And these asymptotic contours are going to be moving at this speed Vg. So what this means is if you apply this transformation to a mode whose asymptotic velocity is Vg, then that mode will be finite on the new coordinate tau, along these new spatial slices tau. So that mode can be squashed down and it will be finite everywhere. But this is only applying to a single mode. So if you like, now we have to assume a particular group velocity of our solution in order to get going with this. Okay, so that's all well and good, but it immediately introduces a new problem. And this problem also comes from the fact that you have a non-relativistic dispersion relation, and that's that the group velocity and the phase velocity disagree with each other. So in general, as you're going out in these contours of constant amplitude, you're actually not going along a contour of constant phase. So even if you choose your coordinates so that you have a finite amplitude on the boundary, when you compactify, you're actually squashing down an infinite amount of phase evolution into a finite space. And so the consequence of this is that you're going to end up with phase singularities at the boundaries of your space, because in general, the contours of constant amplitude don't agree with the contours of constant phase. So the way we resolve this problem is by another parameterization. We introduce a parameterized phase rotation of the field. So we introduce a new field, which is phi hat, and this field is phase rotated in such a way that you're essentially changing the phase of the field so that along this contour of constant amplitude, you now have a contour of constant phase as well. So you're just changing the phase of the field in order to move the contours of phase in that space-time diagram. And intuitively, the phase that you have to scale that by is proportional to the mismatch between the group and phase velocities, which is just to say that it's a direct feature of this dispersion relation. Okay. So having done that, you end up with an equation of motion, which looks something like this. And you'll notice there's an x squared in front, so this looks a little bit different from what we had before, but I'll get to that in a moment. The important point here is that these J1 and J2, these operators, are now parameterized by Vg and Vp. And that should ring some alarm bells, because what we're trying to do here is we're trying to extract a QNM spectrum, and the QNM spectrum is made up of a bunch of complex numbers. So that's two real parameters that we're interested in extracting. And what we're saying is, in order to get out those two real parameters, I have to insert two real parameters that I know ahead of time, which are the group velocity of my solution at infinity and the phase velocity of my solution at infinity. So that's sort of, there's no such thing as a free lunch. I'm putting in two real parameters to get out two real parameters. So that's something we'll come to, but I'll just leave that hanging in the air for the moment. If we look at a particular example, such as the Purcell-Teller potential, then we can get out expressions for these J1 and J2 operators. We see that they're purely spatial operators, and we see that they are in fact parameterized by the group velocity and the delta. And so that's come into the equation of motion through the phase rotation and through the parameterized coordinate transformation. Okay, so we're going to talk now about the presence of this x squared at the front. What we want in order to express our problem as an eigenvalue problem is this equation over on the right, but we need to work out how to get from the left to the right. I tried lots and lots of things to try to get rid of this x squared, but after a lot of work came to the conclusion that it's not actually possible to get rid of it. You need to find some way of getting around it, but it's always there. The reason it's essential is because this x squared is ultimately coming from this expression here. So this x squared is actually specific to the Purcell-Teller case. In general, it takes this form here, where it's essentially a derivative. The important fact is that it goes like a derivative of the height function. So in the relativistic case, you don't get just this function, you get an additional part, which is coming from the fact that you have a partial tau squared in your equation of motion. Whereas in the Schrödinger equation, we had an I partial tau, and that meant that we don't get an additional contribution here. So whereas in the relativistic case, this was an always positive quantity, for us, it's merely a non-negative quantity. And in fact, because the height function has to turn around in order to go outwards in both directions, this necessarily vanishes somewhere on the space, which means that it's never going to be possible to divide through by this prefactor and obtain an equation of the form on the right. So we have a sort of necessary divergence coming from that. So we have to find some other way of getting around this. The way that we get around it is that we find if we repeatedly differentiate the equation on the left with respect to space, so if I look at this equation again, this one up here on the left, if I repeatedly differentiate this with respect to space, then on the right, I have nothing but spatial operators still. And on the left, I have some polynomial multiplying by derivatives of this d tau psi. So what I can do is, if I evaluate at x equals 0, I can kill off everything on the left except for a single derivative of d tau of psi evaluated at x equals 0. And since I can do that for every single derivative in space, I can actually reconstruct the field with a power series. So that's the idea there. And by doing that, I end up with the field on the left, the d tau of psi hat, and on the right, nothing but spatial operators, which is what I desired. And then I can just repackage those as L1 and L2. In practice, it's actually more efficient to first take that equation and split it into two pieces, the pieces which are divisible by x squared and the pieces which aren't divisible by x squared, since the pieces that are divisible by x squared give a nice simple form. So we can get a form of what we're looking for originally just by dividing through by x squared in those pieces. The remaining pieces, they go back to the form that we had to deal with using a power series ansatz. So in this way, we can go from the left to the right, where we get what we already wanted from the simple terms, and then we have to use the power series method on these more complicated terms. But in doing that, we arrive ultimately at an equation of the intended form. We can then express this as an eigenvalue equation, as before in the previous method. The difference now, so we're coming to this now, the difference is that this is now an implicit eigenvalue equation rather than an explicit one. So the matrix L is no longer just a matrix of multiplications with x and derivatives and that sort of thing. It's now parameterized by the group and phase velocities. Now, in a relativistic system, the group, the velocity, and the phase velocity, as I said, they're all just the speed of light. And so they have no particular relationship to the frequency. But in a non-relativistic system with a non-relativistic dispersion relation, these are actually related to each other. And so what it means we can do is we can take Vg and Vp, and we can re-express them in terms of the real and imaginary parts of this frequency that we're looking for. So we can think about this operator as actually being parameterized by the frequency. And then when we do that, we've arrived at an implicit eigenvalue equation. So now we have a dependence of frequency on the left and on the right of this equation, using this relationship between the frequencies and the velocities. But the important thing is that this uniquely defines the QNM frequencies that we're after. So then we discretize in the normal way, and we arrive at an equation to be solved. So we want the determinant of this matrix to vanish. And if we calculate this determinant out, then we're going to arrive at a big polynomial in terms of this frequency that can then be solved numerically. And one of the important points here, so I introduced this power series. Of course, it's a series, it goes on forever, infinitely many terms, which isn't great. But because of this discretization, we actually find that the power series is going to truncate. And it truncates because the derivatives that were appearing in this power series get replaced with Chebyshev differentiation matrices, and these zero out after a certain number of multiplications. And that's because these are effectively differentiating polynomials, and these polynomials, if you start with a finite order of polynomial, will eventually vanish after sufficiently many derivatives. So this is important, and this is actually one of the big differences between this method and the relativistic method. In the relativistic method, you only have to go up to a finite number of these Chebyshev differentiation matrices, 2, I think, and then you're done. And it's the same for every resolution that you treat. But in this case, the number of Chebyshev differentiation matrices you need to use in terms of their order actually increases with the resolution. And so that's one of the features that probably makes this a little bit more computationally intensive than the relativistic method. But I can say a little bit more about that. You then employ a method of numerical solution. One of the things you can do before that is you can recognize that this 2n by 2n matrix here can actually be reduced to the determinant of an m by n matrix, which we call M. And in the case of the Purcell-Teller potential, it looks like this. This is the expression you get out. This V tilde here, you'll see this V tilde here, which is encoding the potential. You also see V1 and V0. That's coming from the fact that when we perform this split of terms, we did a power series expansion of the potential. And so the first two terms were indivisible by x squared. That's why they appear inside the power series. But the rest is divisible by x squared. And so that gets shuffled into this v tilde term. So this is really for any potential that has the same boundary behavior as the Peuchat-Teller potential, so that the Hive function is capturing the right behavior. So you could vary that, and in fact we do that later on in order to look at perturbed Peuchat-Teller and a couple of other potentials. One point that I would like to make, this is just an example of how the matrix looks if we're working, say, just for n equals 4, just so I could fit it on the page. If you look, every single term in here is a polynomial, and in particular, it's a quadratic, and it's actually a quadratic in the square root of omega. So when I was talking earlier about this analogy that exists between the relativistic and the non-relativistic cases, in order to go from the non-relativistic spectrum to the relativistic spectrum, you had to take a square root. And so I find it an interesting little fact here that this square root omega is appearing here because that's the frequency you would get if you were in the relativistic case. So at some level, this problem seems to want to be a relativistic problem, or seems to recognize that it is at base, at heart, a relativistic problem, which I find interesting. So just a review then of what the actual steps of this method look like beyond the naive approach. We start with a parameterized coordinate transformation, where we change the contours of the height function in order to match different group velocities. We then have to do a parameterized phase rotation in order to remove phase singularities. We perform the reduction in time. We then have a power series construction in order to avoid a divergence coming from turning points in the height function. We then obtain an implicit eigenvalue problem where we have a parameterization that's coming from these group and phase velocities that we inserted at the beginning. We then discretize, and then we employ a numerical solver. And so that's the overview of the method. These are the changes we had to make in order to make it work. And I'll show some applications now. So Peuchat-Teller, this is just a sec-squared potential. So here are some results from the method. This is for V0 equals 0.4. So the blue diamonds here are calculated using the method, and the green crosses here are the exact values, which are known from the analytical formula. So you'll notice that the shape here is a parabola. That's corresponding to, in fact, you can see it behind Anil in Anil's picture, the plot for this. Along the bottom, you can see the Peuchat-Teller spectrum that we're familiar with from the relativistic case, which are these two vertical lines. Well, as I told you, the transformation is a square or a square root between these two, and that's what transforms these lines into the parabolas that you see here. So for v equals 1, you see that we recover these very nicely as well, and also for v equals 4. And if you look at the error of, say, this plot here, v0 equals 1, then the error is very, very small and very, very stable. So for very high overtones, we're able to extract these results with very high precision. So one of the other things that people are interested in looking at is perturbations to these potentials, and this is connected with this black hole instability work. So here I'm looking at a perturbation. This is just a low frequency polynomial perturbation to the potential. And I calculate this here, epsilon is 10 to the minus 10, so it's a very small perturbation. You don't see any particular shift, not at least on the level of this plot. If we increase that, then eventually we see deviation. So now the calculated values are, after a certain overtone index, they're shifting away. Whereas before that, they seem to be a very good fit, much less than order 1 deviation. And as we increase the size of that perturbation, then we see that the overtone index at which this deviation sets in moves right back. And of course, this is sort of happening in a continuous way. So just to look at the error there, we see that the error for this 10 to the minus 8 perturbation is growing by orders of magnitude as we increase the overtone index, which is compatible with work on this black hole instability. Just another potential. This is an interesting one for us working in experimental optics, possibly less interesting for black hole physicists, but for the purposes of putting this into an optical fiber, this is an interesting thing to do. So if you put two solitons into an optical fiber, which are slightly displaced from one another, then at least, of course, they wouldn't be solitons anymore, so they would now have some time evolution. But over short fiber lengths, this would be a reasonable approximation to the potential that probe light would see. And we can calculate what the QNM spectrum looks like. So this is for a separation A, which is very, very small. And you see that for the low QNMs, for the low QNM frequencies, there's very good agreement. And then they start to slowly deviate for higher overtones. If we make that separation larger, then we see again they agree for low overtones, but then deviate a lot for higher overtones. And then again, if we make that separation sufficiently large, then we see deviation basically immediately, which is interesting. So one of the nice things about this is that this is potentially within experimental reach. One of the nice features of this potential is that, I mean, obviously, how much of the QNM spectrum can be extracted isn't necessarily, within experimental reach. That's a question for the experimentalists. But one of the interesting things about this potential is that there's now this well between the two peaks, and so there are interesting things about quasi-bound states and quasinormal mode frequencies that arise here. Okay, so that's everything I wanted to say about the Schrödinger equation. And I'd like to talk a little bit now about what happens if we go beyond the Schrödinger equation. So what I have here is a generalized wave equation, where now my time derivatives and my spatial derivatives are given by some polynomials, some finite polynomials. And motivations for wanting to look at an equation like this. So when we're talking about these analog gravity systems like light and optical fibers or Bose-Einstein condensates, we're primarily working within a non-dispersive approximation. So that means that we stop at second order in the spatial derivatives and we don't go beyond. But if we were able to generalize and apply methods like this beyond second order in the spatial derivative, then we could go beyond the non-dispersive approximation and we'd be able to model experiments in more realistic ways. In addition, we'd be able to look at systems which are sort of fundamentally dispersive, and that would then include hydrodynamic vortex flows, which occur in analog gravity. So the Silke Weinfurtner's group in Nottingham has done work on classical bathtub vortex flows, where they've looked at QNMs and extracted them. And then more recently, they had a nice paper in Nature where they were looking at this quantum vortex flow in liquid helium. And again, this was sort of fundamentally dispersive. So treatments of fundamentally dispersive systems would be needed there. There's also interesting questions about black hole instability. So we're familiar with this idea that there's potentially an instability if you perturb the black hole potential. There's an instability in the spectrum. But we could ask the question, well, if we were to include some weak dispersion into our theory, then would the spectrum also see some kind of instability? What happens to the spectrum if I include a very small amount of fourth order dispersion, say? And there are theories of Lorentz violation in quantum gravity models. And so that likewise, this would involve treating higher derivatives in your theory, or at least it can do. Another motivation is just simply the generalization of the QNM concept often leads to new questions and then potentially new insights as we generalize questions. And another, for me at least, is that there's a rich phenomenology in QNMs when you extend it to higher order operators, which is just sort of intrinsic interest. It's a nice mathematical system to play with. So a little bit about the status of mode analogies then. So we had the analogy between the Schrödinger equation and the black hole, the wave equation, and that analogy was based on the idea that we could just simply, at the level of modes, we could take the omega and replace it with an omega squared, and it didn't really make much difference. We can do something similar here. We can't relate back to the wave equation or the Schrödinger equation because the spatial derivatives are different, but we can always just turn this into a generalized Schrödinger equation because the frequencies are just related by some polynomial transformation. And so going forward, we only really need to look at generalizations of the Schrödinger equation. So that's what we'll do. So the QNM problem for a generalized Schrödinger equation, we start with this wave equation. Again, we take a mode equation with a mode ansatz, and then we want to impose boundary conditions. And from what we did in the Schrödinger equation, we have an intuition about how to proceed. What we're going to do is construct a continuity equation. And you can construct a continuity equation for this generalized Schrödinger equation. It's a bit more complicated, but it's not difficult to prove that this is right. And then the boundary conditions, the way we define the QNM problem, is to say that this current has to be directed outwards at the boundaries. And so that's ultimately all that we're asking. Now, there's as I said, there's a rich new phenomenology that comes along when you do this. And this is ultimately a consequence, again, of this higher order dispersion relation that we have. So this is the asymptotic dispersion relation. So you lose the potential because you're far away. And because this is now higher order in K, it means we're going to end up with M modes, where M is the highest power of K that we have. So we can look at an example. So this example captures the Schrödinger equation and the wave equation. M equals 2. We have a second order spatial derivative, and that means we have two local modes on the left and two local modes on the right. And the QNM boundary conditions are very simple in that case. The QNM boundary conditions just say that this current J has to be outwards. So in this case, we're selecting these orange modes, and we have to kill off these ingoing modes in some way. So that's nice and simple. That's the case we treated. But we can look at other examples. So if we had m equals 3, so we have a third order derivative now included. Now we have three modes on both sides. And so we could have either two modes going left and one mode going right, or we could also have one mode going left and two modes going right. So now we have two different kinds of QNMs as classified by the number of modes that we have on either side. And the way that these arise is going to depend on what the solution to your dispersion relation is for a given frequency. So I imagine I'm somewhere in the complex plane, I take a particular frequency, I solve the dispersion relation. That's then going to tell me which of these two cases I'm in, and then that's going to determine how I impose the QNM boundary conditions. And if we go even higher, it gets more interesting. So we have here three modes on the left and one mode on the right. We could have two modes on the left, two modes on the right, or we could have one mode on the left and three modes on the right. And again, as I wander around the complex plane of frequency, I'm going to be moving from one of these cases to another. And so what this means is that for these higher order theories, there's now a classification scheme of different QNM frequencies, depending on where you are in the complex plane. So just a little bit on how the boundary conditions come about. If we now think about this in terms of scattering amplitudes, say I have the A's on the left and the B's on the right. Well, the QNM boundary conditions say that these ingoing modes have to be equal to 0. They have to vanish. So I could just simply choose A1 through A3 to be 0. And that actually exhausts my freedom at the level of just choosing amplitudes. So A4, by choosing the amplitude of A4, I just scale the problem in size. And so that doesn't make any difference. That there's no way for me to kill off B4 in that way. So whatever the transfer matrix gives me on the right from A4, that's what I have to live with. So you might wonder, how is it that we get the QNM frequencies out? And the answer is that B4 is actually dependent on frequency. So these transmission amplitudes in the transfer matrix, oh, sorry, that would be in the scattering matrix, but in the transfer matrix, these coefficients depend on frequency. And so as I move around frequency space, eventually I will find some resonance, which are these QNM frequencies, where B4 will vanish. And then that's going to describe my QNM solution. So that's the picture, and that remains true even at higher order. However, if we look at a case where we have more than one mode on either side, then things get a little bit more interesting. So now if I have, say, two modes on the left, then I can choose these two modes. I have a new freedom. They can conspire together, and I can use that to kill off one of the modes on the right. But then I'll always be left with a final mode that I need a resonance condition to kill off. And you might ask yourself, well, okay, maybe I could choose A3 and A4 to kill off B4, and then I'd have a resonance condition for B3 that would then give me QNM. So maybe that would generate a new set of QNMs. But it actually turns out it's always the same resonance condition that you get out. And in fact, you can express this in terms of the transfer matrix. If you have a transfer matrix like this, and you have T1, which is acting just on the ingoing modes, acting only on the right-going modes, sorry, and then T4, which is acting only on the left-going modes, then the condition is that this submatrix T4 has to have a vanishing determinant. And that's the unique condition that will give you QNMs in the case of these higher order theories. And in the case of just the two-dimensional system, then this reduces to the familiar condition about divergent scattering and transmission amplitude. So we can consider a nice simple case. If we look at a system that just has monomial dispersion, so we have just a single derivative up at some higher order, and we look at the box potential, then we can actually calculate, these are some preliminary results, we can actually calculate what the QNMs come out to be. We can do this all analytically, or at least we can get to an analytical formula that we then solve numerically. So these are the cases for various different M's where we have a single mode on the left. And we can also consider what happens as we go to additional modes. So I could say, well, what if I have two modes on the left? What if I have three modes on the left? And as we do that, we're moving into territory that only exists in these higher order theories. So these higher classifications of modes, these other different types of modes that only exist for higher order theories. So I think this is really nice. It's a nice, interesting phenomenology that exists up at higher order theories. that doesn't exist at second order. And so being able to explore this numerically, which is something that could be done by generalizing the hyperboloidal method, is something that I'd be very interested to look at. So I'll move to my summary now, what we've talked about. So I talked about Schrödinger quasinormal modes. So that was a generalization of the QNM concept to the Schrödinger equation. And that involved setting up a continuity equation to impose these boundary conditions. A direct application of the hyperboloidal method. So we have this route going via the mode analogy, but we can go more directly now using this method, which involves parameterization. First steps towards doing this for higher order equations. So if you attempt to do this, and this is what I'm presently working on, if you attempt to do this for higher order equations, you encounter a number of problems along the way, which some of these are already now solved, but having done the Schrödinger equation. And then I talked about how you generalize this to higher order equations. So at least generalizing the QNM problem statement in terms of this continuity equation. And then also just pointing to some of the interesting phenomenology that you see in these higher order theories. Okay, so I'd like to say thank you again. This is work that has been done as part of this group at St Andrews, the experimental optics group. So Frida there is my supervisor, and then that's the rest of us. And yes, this work was based on these two papers. That's me. So thank you very much for your attention. Thank you.